Okay, I think we'll get started. Hey everyone, welcome again. Another Thursday, another learning session from Egen, and we are here to present one more uh, idea, one more learning experience from our working at Egen in this cloud collective. So let's get started. I'm Praveen Salitra, Head of Technology here at Egen. Uh, and today we have Shri again. Last week as well, he did the meetup on Elastic fundamentals, and today he is going to be presenting or talking about some advanced concepts of Elasticsearch itself. So before we get started on that piece, let's talk about Egen. At Egen, we have been handling and working with the distributed systems such as Elasticsearch and helping our customers and other internal projects as well go through all this kind of things as well, including Kafka and Kubernetes and a lot of cloud services as well. So if you are interested in working or finding out what other things are we are working on right now, hiring is always open. You can go to egen.solutions/careers, and then of course I definitely believe you can find a role that suits your experience and your growth in the next few years. So let's get started. I will give it over back to Shri, and he's going to be talking about some advanced concepts of Elasticsearch.
Thank you so much, Praveen, for the introduction. So hi everyone. Thank you for coming back. And so this week, if you're coming here for the first time, and if you missed the last session, we actually went over Elasticsearch and different comparisons between SQL and Elasticsearch. So this session is going to be a little bit more in depth about Elasticsearch and how things work internally. So hopefully you would get a much bigger idea about what happens, internally in Elasticsearch. And also, if possible, I'll probably give a small demo about different cluster states and everything. So how we can come out of red state, and just like a high-level introduction today. So my name is Yash Datla, as Praveen introduced, and I'm working here as software engineer at Egen. So without delay, so let's get started. So let me begin with the origins of Elasticsearch, right? So the origins of Elasticsearch is, if you observe last session, or wherever, if you found about Elasticsearch, you could actually see that Elasticsearch depends on something called Apache Lucene, which is a free and open source search engine library written in Java by dog cutting. And it actually it's a powerful Java library that is out there. It gives you, a lot of search and index-based operations, and those documents can be coming from, web pages or a document store or anything. So this particular Lucene library is being used for so many different companies as well. So this Apache Lucene mainly works on something called inverted index, which we're going to, hear the term a lot. Actually, whenever we talk about Elasticsearch, what are the internals of it? So just, have that term as inverted index in your mind registered, so that we're going to talk about it pretty often. Some of the major features of Apache Lucene is like it provides the ranked searching or the relevancy of a document, and also it provides automation updates and retrieving of the documents. So let's see who all uses Apache Lucene, right? So these are the major companies which use Apache Lucene. I mean, these are just like, when we did SE research, they're like top known companies. There are many more. We just included a few here. One small thing I wanted to chip in here as well. So we always talk about that Elasticsearch is built on top of Lucene. Not going deeper, but there is one more thing which is built on top of Lucene, which is called Apache Solar. And there is no logo for the arrow mark, but just like to show you that top companies or the daily tools that you use, like Slack, right? Even the Bloomberg, which is like a more data analytic company, those use Apache Solar, which is again built on top of Apache Lucene functionalities. Okay, so just to give you an introduction of what is Solar is, we're not going too much into it. So Elasticsearch is actually also built on Apache Lucene. Let's see what happens when you what are the different stages, right? So that happens when before you create or before an inverted index gets created in Lucene. So in this small diagram here, we can see that the data can actually come from a PDF file or an HTML file or text file. So what happens then? Whatever the data or the words or anything that is inside those files, those get converted to a plain text, right? So because Apache Lucene is majorly a text search and analytic, not analytics, basically text search and storage library, right? So it gets converted into plain text, and then there are a lot of analyzers that will be run on top of this data. Okay, after those particular data has been run, or the analyzers have been run on the data, so those texts will be converted into tokens, right? And those individual tokens will be converted, out of those individual tokens, terms will be created, and those terms will be used to actually create an inverted index. So we're going to, the next slide is going to give you much more clear understanding here, but I want to chip in here is that we at Egen, we actually have, a lot of expertise dealing with this document cracking and also web search and also enterprise search, especially. So we day to day, have dealt with, how to crack a document, how to, find words or in large documents or enterprise search and other things. So we actually do this probably, in our day-to-day operations at different clients. Whatever the theory that I told, let's see the visualization here, right? So let's see there are 3 different documents, right? And when there are 3 different documents, and if you can see, the bright blue butterfly hangs on the breeze, and there are different texts in document 2 and document 3, right? And on the right destination, right? The right destination that you see is actually where the documents get stored. That is what the inverted index is. But before you just skim through the right and then directly go there, identify what's happening in between the stop word list, right? Stop words are those words in English where like da, a, and those words which can be included or excluded from a particular a sentence, right? Those are just there so that you can connect the dots between different words. You get a context out of it. What's the tense? What is an object and stuff like that. So what analyzer, this particular example that we have, is a standard analyzer in Lucene. What it does is it removes those stop words in between, right? And it stores in an inverted index, okay? So how it is storing is, so once it gets 3 different documents, or it could be 300 or 400, right? Doesn't matter. For each individual term that it's getting, going back the list of steps that we went through, after it gets the terms right to create an inverted index, for each individual term, it creates kind of like, I think if you're aware from Java or any program now, it's like a hash map, right? Or it's kind of a table, but you get an idea. Just if you see term and document relation there, it's a string and it's a map of integers. It's an array of integers, right? So it stores all the document IDs where that particular term is present, right? So if you see, okay, so if best is actually there in document number 2, bright is there in document number 1 and document number 3, so on and so forth. Now imagine this wasn't the case, right? Imagine this wasn't how they indexed. Like question could come, okay, why did they come up with inverted index, right? Let's go with the straightforward indexing approach. For each individual document, I save a document ID 1, and I save like all the list of words that come in the document. Like document number 1, like I am kind of reversing the way I'm storing this hash map. The key will be the ID, document ID 1, and the values will be the individual tokens like bright, blue, butterfly, hang, and stuff like that. If the design was in that way, how difficult it could have been when you're searching for a word, right? If I'm searching for a word called bright, I have to actually go through all the elements in that map. And again, in that case, like each individual entry in that map and then iterate or find that particular, oh, whether this all list of keywords, this word called byte exists or not. So that would be too extensive or not efficient solution, right? So that's the origin, or maybe that's why they thought like inverted index is much easy. Now, when you ask for, okay, give me documents where blue or best contains, right? In that case, it's easy for me. Okay, I'll again uh, divide these words that you're giving me in the query. Okay, blue. Okay, where does it blue exist? That blue exists in 1 and 3. Okay, those 3 done. Then what about best? Right, best exists in 2. So I will return you documents 1, 2, 3. Right. In other way, let's say I want a document which consists, or I'm searching for a document which consists Win. Right. Now, I was telling the other inefficient, probably straightforward approach, like direct index approach. If we remove that out of equation, here it's so easy that I can just see, okay, Win, where does it stay? Like it's just in document number 2, right? It is here, right? Now, this is how powerful the search is available in Lucene. Okay. The next, probably before you go to the next slide, right? You probably would be thinking, oh wow, I know Lucene is so powerful. Then why can't we use Lucene itself? Why there is a need for Elasticsearch? One of the main problem is, of course, I think most of us here already are aware of distributed systems, right? Where there is no particular vertical scaling cannot work, because of distributed systems. When vertical scaling is never a good solution with respect to how efficient your system could be, because a single system, like even though let's say my load on my Lucene, I install a Lucene in a single system, and then the load keeps on coming. I'm like, okay, increase more RAM, right? First of all, I don't think it's possible or not, but even then, there is no particular limit. Now, what if that node shuts down? And like my business is impacted, right? So vertical scaling, you just take it out. Let's go with horizontal scale. Okay, my API is there, right? And currently, I have a single tenant or a customer who is indexing at, let's say 1x indexing speed, which is like normal speed, right? I have a Lucene index or Lucene instance in a node. So far, it's good. There are no issues, right? So customer is happy and everyone is happy and we are getting the data. Customer, like more customers came in and your API is actually trying to index double the speed of the index, what it used to be, right? Now, what you would do is like, okay, create one more Lucene instance. So this is how horizontal scaling works, right? Even with, for example, if you're aware of AWS and stuff like that, so all the cloud systems, you actually vertically scale. Horizontally scale, right? You give more systems to it whenever the load is increasing. But this is never an optimized solution, because even this, doing it on your own, especially with Lucene, because when the indexing speed more, it gets increased little more than it used to be, you have to have this constant hassle with respect to managing and maintaining this individual Lucene instance, right? So this becomes an issue. It could become an issue for sure, because you have to first understand all the technical difficulties of managing Lucene in large scale, and also scaling it so easily, right? Whenever you have a new load, right? How do you scale it easily, right? So that will be so tough too. Now let's take a step back. Oh, like this session is about Elasticsearch. So far we're only talking about Lucene, right? So what if I said there is a single service which is like a standalone service, which creates an abstraction on top of Lucene, and that handles all the search and indexing operations, and it also intelligently scale, the Lucene instances internally, so that you don't have to worry about handling this all on your own. Enter Elasticsearch. Okay, so here in Elasticsearch is what you're seeing in between. It's like an interface, right? All the requests that come from an API goes to an Elasticsearch, and it maintains individual Lucene instances. Okay, so this is like actually high-level introduction about Elasticsearch. So this is Elasticsearch is basically the entry point or like an interface for you to handle Lucene instances. Now, the next coming slides will be actually what the actual terms of these arbitrary words that we are using here. A Lucene instance is something called shard in Elasticsearch world. Each shard in itself is actually a Lucene index. So if you go back, as you see, so it's the same Elasticsearch, same Lucene, but in Elasticsearch world, each individual Lucene instance is actually called a shard. Okay. Now, again, this seems good, right? But what if there are like lot of data requests that you're getting, right? Either for indexing or for retrieving or any of those operations, like basically your load got increased. You definitely can't have a single Elasticsearch instance to handle all of that. So what would you do? Enter nodes. A node is nothing but a node is a single instance of Elasticsearch running in it. So each node actually is an Elasticsearch instance. Now, when single instance of Elasticsearch runs as a node, these nodes, as you can see here, a node can contain multiple shards, like two here, or a node can contain just one shard. That is also possible. Whereas shard internally is a Lucene instance, right? Now, this API, when you hit a API request, it can go to any node, right? And let's say you hit API request for a data which is actually there in this shard, right? This hypothetical, right? You want to get the data out of that shard, the shard in the top right. But let's say you hit a request in this node, still you'll get the results. How? Because these nodes, when you create a node and these nodes together, they communicate using a transport layer communication. And they share something called the information about the cluster, about whatever the common system in something called cluster state. This entire thing is called a cluster. So it's as simple, to understand is a cluster is a collection of nodes, right? Where these nodes actually communicate with each other about the cluster state. They also know, okay, which shard contains what. Like when they get a request actually from an API asking about a document in a particular shard, they would just need to, communicate with each other to identify where the shard is and get the data out of it and send it back. This whole thing is called a cluster. And the reason we call this as a cluster, but how do we join these nodes to make it as a cluster? That's a common question, right? Like it could be like my node is running somewhere else. Like how do I make these nodes, group them together as a cluster? They all would store, of course, making sure that the network connections and all are good. Also, they also need to make sure that all of those Elasticsearch instances that you run in individual nodes needs to have the same cluster.name. All right. So only then that the group of nodes will be part of this cluster. Now, we talked about the internals pretty high level, right? So we actually talked about what is a shard, what is a Lucene instance, what is a node, and what is a cluster. But as this is probably an internal, right? If you're just opening Kibana, which is like an IDE or a UI as an interface for your Elasticsearch operations, you probably won't see you probably won't create a shard. You would create, in other words, but you probably won't do operations on a shard directly, right? So what is the thing that we all know in Elasticsearch? is an index, right? So that come, oh, before all that, I think I can go there. I think I missed it. Before that, let's go with this one, right? If you look at this, the primary and the replicas, the fault tolerance. Yeah. So here we talked about this. Okay, we have nodes, we have shards, all good, right? But Elasticsearch is not just doing that. It is the reason it's called distributed and resilient is because of its fault tolerance ability, right? Let's say this shard goes down, or it's right. You don't want the system, you don't want the data in it to go down, right? You want to have a backup, you want to have a resiliency for your data, right? So the first approach here is, let's say I'm having two nodes and I'm storing two shards in it, S1, S2, S3, and S4. Now, if node 1 dies for some reason, right, my data that is stored in those shards are actually gone too, right? So that we wouldn't want that, right? So what Elasticsearch does is it maintains this fault tolerance and resiliency with something called primaries and replicas. All right. So the second diagram that you're seeing here is P1 is like a primary shard 1. P2 is actually primary shard 2. Okay. Whereas R1 is a replica shard 1 and R2 is replica shard 2. So let's say here there are 4 different shards altogether, right? So there are 4 different shards. In this example, in the second one, let's say there are only 2 shards, but instead of just 2, I'm actually creating a replica for each. So for P1, which is a primary 1, I'm creating a replica called R1. Okay. P2, which is like primary 2, primary shard 2, I'm creating a replica called R2. Right. Now with the second approach, we are getting a lot of advantages, right? So we don't, let's say hypothetically in both the scenarios, the first and the second, node 1 goes down, right? If node 1 goes down, as I was saying earlier, you lost all the data that you have in S1 and S2, right? Because the data is gone, right? But in the second example, if node 1 goes down, right, you didn't lose your data because the copy of your data, which is there in P1, is actually maintained in R1. The primary one, whatever the data that is there in the primary one, is maintained in R1, right? Similarly, the copy that you have in P2 or whatever, let's say you're worried about R2 here because node 1 is down, right? Whatever the data that is there in R2, you don't have to worry about it because the data that you have in R2 is actually the copy of what we have in P2, which is primary shard 2. So this approach is called, like primaries and replicas, is a way to ensure that even though there could be node failures or node going down or any hardware failures, your data is still in place. Okay. Now, this one major important thing, right, is like if you see here, Elasticsearch smartly enforced this strict rule that it would never ever, okay, allocate the primaries and the copies of it, which is called replica, in the same node. Okay, so if you look at here, we have primary one, but we don't have a replica one of the primary, right? We have replica here. So it's vice versa. Again, in this example, P2 is here, R2 is here. So this way you can be guaranteed that one node going down, or if a primary goes down, your replica would be there. One disclaimer there: you can make a replica as 0 if you don't care. No, it's all about all these settings, but you can't create primaries more than other than the creation time of a particular component, which we'll talk later. Now coming back, the next slide we're talking about is like Elasticsearch index, right? So if you look at here, I put a small snippet of how it looks like. And here, the left side is the operation, the right side is an output. But if you see here, I'm creating an index, all good. But the settings that I gave here, the number of shards, index dot number of shards stands for primaries, and index dot number of replicas stands for the replicas, right? So I was just giving an example earlier that it's completely your wish if you don't want any replicas. If you're okay if this primary goes down, and if you're okay with losing the data, it's all in your hands. But then let's say tomorrow, for some reason, you want to have more number of primary shards. It's not possible because the number of shards, which is nothing but the primaries, could be only created only at the index creation time. It cannot be modified later. But the number of replicas can be modified later too. So here we saw an output of the creation. I just got the settings, and I also have an output of what the health looks like, or this just the index, and also what is the primary count 1, replica count 0, what is the store size. The index is of course a logical grouping of primaries and replica shards. So whenever you are actually whenever you're creating an index, it's actually creating shards internally. Okay, index is just a logical grouping. When you delete an index, it's actually deleting the shards. So it's just that. So you as a user, as I was saying earlier, as you're just doing day-to-day operations on Elasticsearch via Kibana, you wouldn't probably see what are the shards. Of course, you can see here shards acknowledge true, but you won't probably create a shard directly. You'll create an index, you'll do operational index, but internally, all the operations that happen, the searching, storing, and indexing, are actually on shards, not the index. This is the order changed here, but this is what we're talking about indexing. Now, if you look at this diagram, the whole impression of index you can probably visualize. Even though I have shards, technically in the nodes, indexing is a grouping of them. Like for example, here, if P1 and R1 are actually shards of, I know, or if as a user of the system, I know if I'm going to create log data inside it, right? I would probably create a log index, right? If P4 and R4 are actually the data of an event, I would create an event index, right? So it's just the grouping that you do is actually nothing but an Elasticsearch index. This is a little more depth. I'm not sure like how many of us would have to deal with it, but I think this could be one. This and the next coming slide would be one normal introduction of how writes work internally of an Elasticsearch. So far, I gave a high-level abstraction saying that, okay, we have a Lucene instance, right? But Lucene internally, or the instance itself, is actually an abstraction again, or the Lucene index is abstraction again on something called Lucene segment. Okay, so segments are the tiniest internal storage elements in Lucene where the index is actually stored. Okay, I know it could be a little overwhelming, but when you think that it's actually storing that in a shard, right? Where shard internally has a Lucene index, but Lucene index is actually having some tiny storage elements called segments. Okay, and these segments are where the data gets stored. Major baseline rule here is these segments are immutable. Okay, and when the indexing speed increases, right? So it goes to the shard, and shard creates, shard sends to Lucene in small segments. Lucene keeps a buffer of the smaller segments, and these Lucene segments are periodically merged into larger segments, and these segments go away. So if I have, let's say, small blocks of Lucene segments, those will be merged together as a big one, and that will be persisted to the disk. Okay, so you don't have to you don't like, okay, I have a small segment, let me just persist to the disk. No, that doesn't happen. It maintains that buffer internally. So it periodically, whenever it finds the resources, it will merge those segments together and persist it to the disk. Yeah, I think by the statement of segments are immutable, you would be able to understand that there is no other operation other than creation and deletion in Lucene level. Okay, even though if you are seeing update endpoint or update API in Elasticsearch, it's not actually doing an update of the segment level. Okay, so what happens internally is, like, as I was saying earlier, let's say you delete an object, delete a document, and that document's come to the shard, and that shard, it marks that particular document as deleted, and the segment gets marked as deleted, and it can be merged to the larger segments and persist to disk. And later it will be deleted in the disk. So the deletion happens at the disk level, not at the segment level. The segment is still are immutable, basically. The actual Lucene commit is very expensive. Okay, so the next slide would probably give you much more idea about what are we talking about in these two statements. I'll probably talk about the Lucene commit the next slide. And then we also wanted to know, or I want to register this term is something called translog or transactional log, where each individual operation that you do or each individual document that you index will be stored inside Elasticsearch. Let's see. Yeah, auto segments go Lucene commits to disk. Now, this is the Elasticsearch persistence model. So I will take some time here to explain clearly here, so that it's helpful to understand. Imagine this first stage here. If you can see my cursor, imagine the first stage here that you are indexing the documents, right? So whenever you're indexing the documents to Elasticsearch, it doesn't directly store that. Okay, of course, I think if you're following clearly, we have a Lucene internally, right? It doesn't directly say, okay, Lucene persist this to the disk. No, right? Because that statement or that commit to the Lucene is very expensive resource-wise, right? And Elasticsearch doesn't want to do that, because if it could have picked up that route, I think it would not be so easy to manage, right? Because a lot of resources go into doing that one commit for each individual operation, and that would cause that would hamper other use cases of Elasticsearch, right? When you're indexing parallelly and stuff like that. So, okay, so when you index a document, so what Elasticsearch does, it does two things. One, it stores the document in a memory buffer. Also, it stores the document in a translog. So it does two things. One, it stores the document in a memory buffer, and it stores the document in translog, which is transaction log. The reason why for a transaction log, we'll go first, then we'll go with the actual document. Now, if you look at the screen here, right, you index a document, you say put test index, blah, 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 ID is equal to 1, student name is equal to, John, for example. When the request comes to Elasticsearch to index a document, before it goes and actually make the document the next operations on the right, it would write in the translog so that the translog itself would be directly written to the disk. Okay, and there is a reason for it. First, if you talk about this is actually the failure, backup kind of a use case. The reason being, let's say for some reason you indexed a document, and before I actually follow the document flow, right? And before I write it to the disk, the node crashed, right? And now your document is lost, right? There is no way for you to, when your node comes back, there is no way for you to get the document, right? Instead, with this approach, you're writing the translog directly to the disk every time, frequently. The reason being, let's say a node restart happens here, right? When a node restart happens, whatever it does this, of course, recover all the committed shards at one time. Along with that, it actually replaces the translog that you actually stored here, right? So in that case, when my document storage flow, before it's get executed, if my node got restarted, the Elasticsearch actually has an option, right, to replay the translog from the disk, which it actually stored in the disk already, right? This is the advantage of using a translog and why it's being written to the disk. Now, this is a backup mechanism. If you take that out, what happens, the normal green path scenario, right? Now, when you, so when you index a document, it comes to translog, all good. But then that document is actually stored in something called document buffer. Okay, it's stored in the document buffer, and the refresh endpoint is being hit. Refresh is an operation where it makes all the documents that are there in the in buffer, also the disk, to be searchable. That is the high level that it does. Elasticsearch by default makes it the refresh interval as 1 second. So when you index a document, even though, let's say, I mean, this is a list of steps that it happens, right? When you index a document, you see an output, and let's say after a second, if you look for the document, you actually see the document. So because the refresh already happened, but it doesn't guarantee that those documents are saved to disk, because as I was saying earlier, it's not that individual operations that you do, like create, index, update, and delete. Those operations are not stored to the disk directly immediately after your operation. Okay. Now, what happens is, like Lucene level, there will be segments, right? We were talking earlier, the previous slide. So whenever you hit a refresh, whenever the Elasticsearch does a refresh of the shards, Lucene hits something called Lucene flush, which whatever the data that is there in the translog, that will be returned to a new segment. Okay, and the translog is cleared. So that is it. Now this is a place, right? Now on the Elasticsearch level, there is a flush that's happening, which is the main operation that happens. Okay, Elasticsearch flush actually does a Lucene commit. So what Lucene commit does is, it actually takes all the changes that are there currently, and it will write to the disk. Now, as you can see here, this writing to the disk operation happens so infrequently. It doesn't happen, after every call. That's why it's actually so resource expensive. Now, there are small set of segments, right? So all those segments will be merged together, right? That will also be written to disk. Now, here, if you take a step back, you don't have to worry about, okay, when should I hit a flush, right? Or sorry, that's it. You don't have to hit a flush. Like when should I hit the flush API? Because the flush is available actually as an API, as an endpoint. Elasticsearch documentation says, basically, even us, we never actually handle these, because Elasticsearch itself, they themselves say that you don't have to do it. It's very rare for you to actually manually flush the particular storage, whatever you have the changes. Because Elasticsearch internally manages this merging of the segments and also syncing them, hitting the Lucene commit so infrequently, depending on the buffer size that it currently has. So I think this is actually a high level, probably a little deep, but this is where the Elasticsearch persistent model comes in. The next slide is about upsearch. Okay, so I think you can see the strike through there. For every operation that you do, it's not actually, or for every updation that you do, it's not actually updating the existing document. Is because that document, or internally the segment, is actually immutable, right? So if you look at here, one of the examples, like one test index, here we have, ID1. Okay, I think I will take it back. So this is like an output. This is output. This is a screenshot of the output window. So I don't have a request body here, but you can get the idea. What the operation that I did is like with this comment, right? I actually created a document in this index, in this type. I created a document with ID 1 with refresh is equal to true. So the reason I'm saying refresh is, I mean, we usually don't do that for every query, is because here to show you the output so that it's immediately searchable. But yeah, so here I did, okay, I want it to be searchable because I want to show you here. I did that and I got index type. All these underscore fields are metadata, even this result in force refresh. Source, I won't get it because this is not a retrieval, right? So I got forced refresh is equal to true because I actually forced refresh it and result is equal to create. Now look at these three terms, right? Version is actually the number of updates that happened on the same document. Now, I think last session we went through high level. There is no way for you to go, if you're at a version 2, there is no way for you to go back to version 1. Okay. So that is like one important thing to note there. So you can get like, roll back a trans. I think last week we went over about the transactions as well, that you can't roll back a transaction just as you do in SQL. Like a document is created or updated, a new version of the document is there. Now, if you look at here, this is an endpoint to just show you. Now look closely at this column called docs.deleted. Okay, so the current status of this index is green, index name, status is open, and you have the primary is 1 index, 1 shard, replica is 0, that's fine. And then I have a document count as 1 because I indexed 1 document, and document deleted is equal to 0, right? Now, pay close attention to the next operation that we do here is I am updating the document, right? I have actually updated the document. I didn't put the request here, but I probably could have updated some name or something. So here I get a version 2, right? Which is pretty clear. And I get a result as updated. Now, if you look at here, the health status or where it shows you the documents currently are there in the index, we have docs count as 1, docs deleted as 1, right? So you can understand that the previous document that is there, it actually got deleted. Okay, so it marks as deleted internally in the buffer. Now, your question could be like, or one doubt could be that how would the search work in this case? Like I created a document and I deleted a document. Sorry, I updated a document, right? But the document still exists in the buffer. It just got marked as deleted. So when a search operation comes into place, Elasticsearch only searches for those documents in the shards where the documents are not marked or not mapped as deleted. In that way, when you search for a document, you only get those documents which are not marked as deleted. Okay. The other two fields are actually, there is something called optimistic concurrence control that happens in Elasticsearch because it's so distributed and so many processes or so many operations can happen on Elasticsearch parallelly. So this sequence number, it wasn't there initially. It actually came probably after a few years of Elasticsearch inception. What they did is like they wanted to have a way for you to know if a particular document is greater than this sequence or not. The sequence here that we are seeing is actually the number of operations. It's not about the document, okay? It's about the number of operations that happened in this index. So that's why here, it's not about the version. That's why you see, and it starts with 0. It starts with 0 here. It happens with 1. They conjunct that with primary term, which is like a little more internal concept, but they conjunct that with primary term so that when concurrent requests come to update the same document, right? And let's say I got request 1 from API 1 to update a document. with the same exact very millisecond difference or even less than that, I have one more request coming for the same. Like let's say a situation arose where there is updates of two documents at the same exact time. Elasticsearch actually throws an exception called, this exact term. So it tells, okay, let's say this request went through first, right? But when this operation tries to do an update, it throws an exception saying, okay, the sequence number and primary term are less than what I'm expecting, so this operation cannot be, guaranteed. So it ensures that the whole reason of this is because if this approach isn't there, the sequence number and primary number, there could be problems that, let's say this is an older version, this is a newer version of the document, and this went through first and this went through later, right? This operation or this older version of the document actually overrides what you have already. So this problem, they solved it by using this optimistic concurrence control. Yeah, each upgrade is actually already. I think we went over a lot of concepts. So let's go with individual ones. Okay, the slides are messed up. Of course, index is a logical grouping of all shards, which primaries and replicas. Where replica is, let me go one by one. I think that's more better. Okay. So here we can see, right? Lucene is actually open source search library, which provides a searching functionality for you. Okay, cool. Segment is the basic unit of data stored in Lucene with the search capability, and also I already told it's a store, right? This is the tiny unit of data store that we can have in the whole Elasticsearch system, or these segments are actually immutable. Okay, Lucene index, right, is actually an abstraction of over multiple segments. There will be very tiny, there will be a lot of multiple segments inside a Lucene index. Lucene index is actually also, they kind of go, they say arbitrarily actually. Some blocks said that segment index is actually inverted index. Some people say that Lucene index is actually inverted index, but it just like, I don't think it doesn't, it's kind of same. At the end of the day, it's just like one inverted index in Lucene. Now we come to Elasticsearch world. The first three is actually Lucene things, right? Internals of the Lucene. Now, if you come to Elasticsearch world, there is a shard, right? Shard is nothing but individual Lucene instance, which has its own running, search operations, storage and stuff. So that is a shard. Now let's go to node, right? A node is nothing but what it does. The node, right? It communicates. A node contains a lot of shards in it, right? And it's like a single Elasticsearch instance, right? Which communicates with those shards. Now you have multiple nodes, and those multiple nodes will be grouped together, called a cluster, right? Now, I think if you saw the diagram where we went through how nodes communicate with each other, there is this information called cluster state. Okay, this cluster state contains the information of all the different states, that the node information about the nodes, the shards, and other things. So that would be easy. So let's say, and I think this I will be able to show you in a demo also. If a node comes down, right, how quickly the other nodes would know the information, right? Because they speak in the transport layer, right? Now, for the cluster state, we talked about different kinds of shards, primaries and replicas. Primaries and replicas, especially, whenever you write a data, right, or index a document, it always goes to the primary shards first, okay? And there will be background syncing operation that happens, which syncs whatever the data that is there in the primary shard to the replica shard, so that both will be in sync, almost like with a very, very, very minute difference of time. So whenever you write a document, you automatically get a backup available. That's the reason whenever you write a document, you actually get how many shards responded to that operation that you did. Now, a replica, of course, we just talked about, is like a copy of the primary shard, and index is a combination of the grouping of all the shards together. One thing to note here probably is, let's say a node went down which is containing a primary shard, right? A node went down a primary shard, but we have the replica of it. There's a problem here, right? If there is no mechanism set up, if a primary is went down and we have a replica available in another node, I have a write operation came in, right? But technically the writes are only supposed to be written in a primary shard. But now for this index, I don't have a primary shard, right? The way Elasticsearch handles it is whenever a primary shard goes down, of course, or a node containing primary shard goes down, it identifies, okay, where are the replicas? Should I promote this replica to a primary? It does that automatically, right? Whenever a primary shard goes down, it will communicate with other nodes, identifies where is the other replica shard, and makes it the primary, so that when you write a operation, the writes are good. Then it will but the node is still down, right? The node is still down. Now, technically, this index, the way you created a settings or the rule for this index that you set up, the job for the Elasticsearch is always maintain one primary and one replica. So it made replica primary. So one thing is good. What about the other primary, right? So it would try to see if there are any available resources, or in other words, like nodes, to set up that extra or the new replica. So this balancing or cluster balancing, we call, is actually done by Elasticsearch so nicely. We don't have to worry about what happens if the primary goes down. So that I think is pretty intense about how we talked about like what are the internals of Elasticsearch and the Lucene and other things. Now let's talk about different types of nodes or different types of roles a node can play, right? As we talked about, I'm just recapping again. A node is nothing but a single instance of Elasticsearch running in it. A single instance of Elasticsearch, nothing but a node, right? A node can play multiple roles. Okay, I think we have a very beautiful depiction of cluster later, but let's go with this. We are talking about high level of important type of roles that a node can play in a ES cluster. The first thing is master. Okay, master is actually responsible for doing all the lightweight operations. Like when you create an index, it's actually done by the master. It communicates with the data node and creates an index and allocates the shards to it. That's it. And also identifying, okay, which nodes are part of the cluster, right? And all those operations are done by the master. Now, when it comes to data node is actually where the data contains or data exists, right? All the CRUD operations that happen go to the data node, not the master. Okay, they go to the data node where you perform the CRUD operations. Let's go to the ingest. This is probably, we didn't go through this yet, and this ingest process also came probably at version 6, or it's not there before, but definitely not in the older versions. Ingest nodes are mainly useful when you actually have something called ingest processors. So simple way to put this is, let's say there is a document. There is a document where, yeah, so there is a document, like, for example, my name, like employee name. But for some reason, the way we index, right? We handle a lot of index processors too. But a common use case of Elasticsearch is like they have an API, they have a data store, they will get the document, do some operations on top of it. Let's say I wanted to add a phone number to it, which is not there, okay, in the actual document that I'm getting from somewhere else. What I would do, probably call, or add a suffix Mr. or something, right? I will do in the Java program or Python or anything or any programming interface, and then send it to Elasticsearch to get stored. Now, ingest processors comes into picture. Let's say for the simple operations, they can be much more complex too. I'm just giving a simple example. Let's say I don't have this Java API in between, right? I have a document, right, which is been coming from so long, right, from a system. Now, I have Elasticsearch. I'm indexing the document, same student name, Sri Harsha, all good. Some business use case came, okay, we wanted to add a suffix or prefix to the name, right? So it would be, for example, Mr. Sri Harsha, right, for example. But the document store where the document is there, you don't want to change that because it's still there. So what else can you do? Ingest processor is something as a starting point before you actually index the data into your index or ingest the data to your index. That is where these ingest processors comes into place. So you this terminology that we use is mostly with what we use similar to ETL. So you have an ingest pipeline, you have stages. Okay, do this stage first. After that, process it. Split it, combine it. All those processes that happen actually in ingest processor, right? So in that case, I can write an ingest processor. I can say what is the index, what is the operation that you do, get the value, add Mr. to it, and then that's it. That's the functionality of that ingest processor, and I will attach that ingest processor to an index. So whenever a call comes through from the external API or something with a document, this ingest processor automatically does the processing and stores it into the index. Now, but this processing, of course, is some resource incentive, right? Or it includes, resource allocation, stuff like that, right? So all those hardware, optimizations are done in an ingest node, so that you actually, if you ever face a scenario that, okay, I probably would need to do a lot of ingest node processing, I would probably create, 2-3 ingest nodes, right? In that way, your data nodes, which is for CRUD operations, is not impacted by this ingestion processing. Your master is not impacted. So other nodes are not impacted. Only these nodes do these operations, and it's much more efficient and performant here. Now let's come to coordinator node. If you see here, the way we gave node.roles here, master, data, and ingest, we told that what is the role that this node is. For coordinator only nodes, we don't give any name in it. By default, like if you don't give any name, it just act as coordinating roles. So what this coordinating roles does is, this nodes does is, let's say you have bulk requests that your system is sending to Elasticsearch, right? Like bulk indexing, right? Or bulk, all the search that happens. What it does, it identifies, okay, where should I go? Which shard should I go, right? To the data nodes. Does that operation, gets it like something like, not like map reduce, but something like that, like search reduce. So it get that, collect the data and then send it back. So if you're seeing a lot of load that is coming to you, it's always advisable, Elasticsearch advises to have 1 or 2 coordinator nodes as well. Now, yeah, this is where we want to show you like a typical Elasticsearch resilient and fault high availability cluster that we have. These two are like major important points before you actually see the illustration. But let's say, yeah, any Elasticsearch node can assume multiple roles at the same time, right? When you create a node, or when you install Elasticsearch for example, in a node, it automatically by default is master eligible, or it performs multiple roles like master, data, and ingest. Okay, but for higher availability, because there is a big process called master node election that happens, which could be a little more deeper concept that can we do in another session, but you don't want this, let's say if you have all the nodes as master eligible, right? And one node, the collected master gets down. We don't want these master eligible nodes try to get a new master elected and later all this cluster rebalancing. You don't want that. That probably isn't a completely right solution. So Elasticsearch, and also we, with our experience with Elasticsearch, definitely encourage or recommend for your huge data load, and if you want higher availability, always run dedicated master nodes, right, in your class. So just name those, give the role of a master to those nodes, and let them, and of course, it should be odd number of master nodes so that you don't have to worry about, again, master election, other things, because it's always between those three. This is a typical example that the next coming points that we're going to see. So we have 3 dedicated master nodes, master 0, master 1, master 2. Then we have 5 data nodes, 0 to 4, like 0, 1, 2, 3, 4, right? Let's say I have, in our organization, let's say I have an index, right? Those index is like primary, if you see, I have, 5 primaries, right? And each replica for each primary. So it's like 5, total I have 10 shards, right? 5 primaries and 5 replicas, right? Now, when I create this index, what Elasticsearch does, currently it's blank. Currently, other than some metadata, even though you don't create your own like customer-oriented indices in an Elasticsearch cluster, Elasticsearch maintains some internal indices, which starts with dot Kibana, dot APM, other things depending on the license that you have. Those are like those metadata indices. Okay, those you don't have to worry about. So now Elasticsearch, now it has to allocate, right? So what it does, okay, now the like first primary shard puts in data node data 0, and then second primary, the replica of it, of course, because it shouldn't keep it in the same node, it puts into another data node. Similarly, the second shard, it puts there because there is no replica of 1 there. The replica goes to the other node. The second, or the primary shard 2, or the third primary shard, the replica goes to another node. Similarly, or node, and then, so if you see here, this structure here, even though one node goes down, I have the replica of that shard already available, right? I don't have to, like, let's say if data 0 goes down, my data 4 is already, data 0 goes down. Let's see that scenario. Primary shard 0's replica, where is it? It's in data node, data 2, right? Second data node. Similarly, replica shard 4 already has a primary, which is in data 4. Now, let's say I have another index, which is index P, right? I have 3 shards primary with their respective 3 replica shards. So this is actually, you have your 3 dedicated master nodes, right? And you have your dedicated data nodes. And of course, here we didn't introduce ingest and other type of nodes roles, because high level, these are the main 2 that we use, in our systems, unless you are using specifically ingest nodes and coordinating nodes. That's a different story. One thing to note is Elasticsearch, of course, if you observe their documentation and their release structure, they actually evolve pretty quickly. And so recently when we went and we saw, there are actually a lot of new nodes that came in their list of roles that the node can play. Like there is like voting only master node, or hot node, cold node, directly they gave. But high level, like traditionally, these are the actually nodes that we majorly use, master node and data nodes, and the other nodes are just fall in place. Let's talk about the statuses here, right? The red, the green, and the yellow status of the cluster. Now, our Elasticsearch cluster actually has an health endpoint, which tells you if your cluster is in a good state or a bad state, to be honest. And they segregated it into three different levels: red, green, and yellow. The one that we are seeing here is green, right? And the reason why it's green, like these statuses and the reasons that I'm going to give you are actually one of many. Like for green, it's of course it's simple, but for yellow and for red especially, there could be multiple reasons it could happen. But this is one of the first and foremost thing which every admin would actually first look into. Oh, okay, why it's in red? Okay, let me. These are the list of events. For your Elasticsearch to be in green, right? All the shards of all the indices that you have, whether it's primaries and or replicas, should be allocated to the nodes. I'll repeat that again. For all the indices that you could have in your system or in your cluster, right? All the shards, whether it could be primary and replicas, should be allocated to a node. Okay, that's when your cluster, your index, all the indices will be green and turn into all your cluster will be green, right? So here, if you see the example, even the screenshot, of course, like this is running my local. I think the instance that I ran that time for the screenshot was like single node cluster, as I put the comment. Here I created a test index and I told the settings, number of shards is equal to 1, which is primaries, and number of replicas is equal to 0, right? So Elasticsearch, because it's a single node, it doesn't have to allocate the replica. So by default, it's just 0. So as long as it's able to allocate this shard of this index, which is a primary, in this node, it's good. That's why you see acknowledge true. Elasticsearch telling you back, yes, I got the operation, it's all good. Shards acknowledge true because the shards, number of shards is equal to 1. That acknowledge saying that, yeah, I got allocated. And index is equal to test index. The next operation I'm just doing a cat operation, like the cat request on the API, the indices API of this index. It's telling you green, right? This health status here, some UUID and primary or replica, other things. Now, when you do cluster health here you can see that the cluster health is actually green, right? And it's all good. Now, let's go to the, yeah, okay, as I explained earlier. Now, let's go to the yellow, basically. Okay, here. Now, the same index, test index, if you follow, here I told number of replicas is equal to 0, right? As I was telling it earlier, there's a single node, right? So it's just a single node. And the only way to continue it to green is to create another index. I can create multiple indices, but only with primaries. If I create one more replica or any of the indices, it will fail because ES fundamentally doesn't store a primary and a replica in a single node. So what I did, as I said earlier, you can update the number of replicas at any point of time you want. Okay, what I did, I actually did update number of replicas is equal to 1. Now Elasticsearch is in trouble because it has only one node, but it has to assign 2 shards, which is a primary and a replica in a single node, right? So it complains or it says hello, right? It says they are hello, and then unassigned shards, if you see, it's 1. Okay, now let's come back to the red status. Okay, this setting could be, it's not there. I think I forgot to remove it. It doesn't complain, but look at this thing, this line. Now for the same index, test index is already yellow. Now I created a new index saying that, okay, so even though I didn't give the parameter, it will automatically create a number of shards automatically. What I did is like, this is little more another concept, which will go in next session much more deeply. It's called shard and index allocation. Where I'm probably give you a little bit brief. For each individual nodes that we are creating, right? Or we are initializing the Elasticsearch, you can give certain attributes in those nodes, right? This is how actually hot and cold nodes work, just like a primer there. So they segregate different nodes with a parameter saying, okay, this node a parameter, just like a parameter, like, here I'm using underscore name. I can use anything like size 50 MB, temperature, warm, just something, right? Storage is equal to hot, something. I create a user like key value pair, like key is some parameter, value is a value of it. Now, the reason we do that is, let's say for some reason, I want an index, right, to actually go to a particular node, or I want the shards of this index to actually go to a particular node. That's when you use those attributes that you created in those nodes, and you tell here index.routing, whatever this index, this route, the allocation of this index of those nodes should contain a name called A, B. It can be, comma separated. So this is, I was explaining, this is a single node cluster that I was using. Definitely that node's name is not A or B. Okay. When I immediately do that, and if you see the cluster health, it will turn out to be red. Okay. Because why? Elasticsearch cannot allocate even the primary itself. Okay, so that is a baseline. So if I go to like all the three, first all the primaries and all the replicas are green, all are allocated in all the nodes, or whatever the conditions that they have, replicas and everything, that it should be green. If primaries of all the indices are allocated, but replica of any shard isn't allocated, then it will be yellow. If any primary of any index, right, is not able to be allocated, then the status would be in red. Okay, so this is basically high level. Now, you can, if you want to ask, like, okay, or a doubt, right? So we have three indices, for example, and one for this index, test index 2, I gave this weird condition where I'm expecting that node name to be A or B. The other two indices, for example, like let's say test index 1, that is still in green, right? Because that index has been already allocated. There is no weird condition for it. The operations still continue to happen on those index, right? Because that is still in green. If you want to read all the operations, that will be good. But for test index 2, you can't do any operations because it's in red state. So that is one important point that you want to note. Yeah, I think start with demo. Let me stop and share the screen again. I think in the meanwhile, if you have any questions, probably you can ask again. Okay, you can see my screen, right? So here, this is running on Docker. If you're aware of Docker, all I did is like last session, all I did was like just to create multiple instances together so that I can give you a demo of what is it, like a multi-node cluster. So here, what I did was like, okay, I can the font size. Forgot the syntax and stuff. How do we do that?
Just zoom in.
I'm using like mouse, so I'm not much aware of this actually.
Can you? I think you can do it from the Chrome itself. Go to the settings of the Chrome and then keep zooming on.
This is Sublime actually. I don't know. Okay.
Oh, we are seeing your Chrome or Kibana actually. Okay.
Oh my God. Okay. So bad. Sorry. Cool. Yeah, you're seeing my
Yeah.
this,
Now
right?
it's Sublime.
Yeah. Yep. So here I'm okay. This is what I'm using right now. The other one is just for the previous session, but I just want to show this. Like basically, I created I use like multiple images and just like using master ES1, ES2, ES3, and of course Kibana. Gave it. This is how we can actually connect the Kibana to your Elasticsearch. I'll just give it this because as long as one of my master the port is set up, that's all good. That's all what Kibana needs. It will be able to communicate with master over there. And I create a network, and then I, of course, create some data volumes. So that is what I was trying to show earlier. But sorry. So here, do multiple operations. So if you see here, we have a master, right? We have ES1, ES2, ES3. If you see there are like there seems to be a lot of new roles that came up here. Earlier it used to be just I think DMI, data master ingest, and I think I'm using 7.12. So it always keeps on changing, but that's fine. So what about indices, right? So I don't have any indices. So let's do the other thing I want to show is like the cool thing is how these nodes communicate with each other. Yeah. One last time. I'm so sorry. Yeah. So to show here as well. So I did a Docker PS, and I'm not going to open all the logs of all the instances, but let's see. So here, yeah, as I was saying earlier, we have multiple instances here. Let's look at the logs of ES1, or which is like one of the data nodes. I can do simply with do this command here, right? So it's just here, and yeah, probably this as well. ES02, right? So currently we are looking at the logs of data node 1 and data node 2. All good. Now, if you look at this, they're always getting new logs. They're always communicating with each other. Okay. Now, let's go and create an index. Yeah. I give 1 and I give 1 again, right? So when I do this, I don't need to know the metadata, so I can basically look for just this one index, and it's green, right? Which is what we need, right? Now, this is just to show you different, the like kind of like the way we can change, So cluster is also green, right? And data nodes are 4 because all those master ES1 data node 1, 2, 3, right? Now let's see. I decided to yeah. So this is the other thing that I want to show. Like let's say if I want to get shards, actually wanted to see where the test index is allocated. So this is an important thing. So because I have just one shard, which is of the primary, the shard of the primary is actually given to ES2, or for example, I think, yeah, data node 2. The replica is actually given to data node 1, right? Now, in the short demo, I want to show you that what happens if data node 2 is down, right? Now, let's see what happens. So this is data node 2, and this is data node 1, right? This is just to show you like how this data node 1 knows the information. So what I would do here, so data node 2 here is here, and I will just do docker stop. The information, yeah, look at this guy. Right. So if you look at here, this information that it gets, where is this? Yes. Yeah. This is what I wanted to show you actually. You can see this information, right? So data node 1, which is a completely different node, actually got the information about data node 2, telling remove ES02. Now, of course, because I stopped it, my logs will be here. Now let's see what happens for the shard allocation. Did you see the primary that you have in data node 1 actually got sorry. The replica that you had in data node 1 actually got promoted to primary, right? So whatever ES01, whatever we have as replica, now it became primary. Because we have nodes, because we have resources, Elasticsearch is actually trying to assign the replica of this index. It will take some time, but it actually created that, like assigned that particular replica as well. Let's do one more thing. I think what I wanted to do now is to create one more replica. Of course, I have to do like this because the index is already there. It expects a settings API to be called directly. Oh yeah, I think I want to show this as well. Now, let's say I want to increase the number of primaries, right? If you're following, I was saying that this is not possible because you cannot update a particular primary shards when it's open, when it's operatable. You can only update the replica shards. So I would give 2, right? Now, I think we can check like this. And also this. And of course, after this, right? This is just to see the output together. So we are just checking first what is the shards, and then we are doing a cluster health, and I'm changing it to 2. And then let me see the shards again and see the cluster health again. So currently it is primary and replica is here, but yeah. So this output, when I try to get all good, this is what we already saw. And here I try to get the health, which is green, all good. But then I did an update saying the number of replicas to be 2, right? Now here it's not, it gave me an acknowledgement, right? But then when I did the shard allocation, because I wanted to have for the primary shard, I wanted to have a replica 1 more, right? It is still in unassigned stage. Now, yeah, the reason I wanted to show you is this guy, the yellow state, where I was telling that if any of the replica of the indices or any of the replicas of the primaries that you have, if that is not being, and that is not able to allocate that, you will get an yellow state. Okay, now let's see again. It's still yellow because I think, yeah, it's still not able to assign it because you have a primary already, you have a replica again. Now let me bring back for some. this we stopped. Is this the one? I think so. Right. So look at this. I want to show. So you have this thing loaded up. You will see that information as well here. I think it's still trying to get. Oh no. Yeah. Yeah. Look at this. So this node, which is data node 1, automatically got the information that this a new node has been added to the cluster, right? So it's telling the cluster name, is also telling this current ES node, and telling what is the node name of, or the information about the new node that's been added. Now what would happen? It got sharded too, right? So now what happens to the cluster state? It's definitely green. So this is how the shard allocation happens, and yeah, this is how information between the nodes happen. So I think with that, let me go back to the slides. Yeah. Yeah. So with that thing, I think we were able to get the, what about the basics of Lucene, and then what are the clusters, node, index, shard, and segments. Different type of nodes information, and I think I just have one reference there. I think we can open up for the questions actually, if you have any questions. Okay. I think Praveen, you can take over.
Cool. Thanks, Sri. Another comprehensive overview, and then of course going in depth with Elasticsearch. So thanks for that. If there are no more questions, we can announce our next meetup. So continuing in the series of talking about Elasticsearch, next Thursday I will join Sri to talk about some of the architectural decisions as a cloud architect that you will have to take when you are thinking of using Elasticsearch. In terms of, so we will go through the brief overview of the Elasticsearch architecture. We'll talk about how to size your Elasticsearch cluster, including high availability, whether you are going to be using it for a small use case or maybe for large clusters. And then we'll talk about optimizations that you can do and you should do on indexes or indices and shards, the index lifecycle management, but then also talking about options that you have in order to host Elasticsearch, whether self-hosted on Kubernetes using ECK operator or directly utilizing Elastic Cloud. So we'll talk about all of those stuff. One more advanced session, of course, and that's going to be next Thursday. So on the same place here. So that's pretty much it for today. Thanks for joining. But looks like there is a question from someone just at the last moment. Question was, is Elasticsearch more generic way related to, in a more generic way related to Hadoop architectures or HDFS?
Hadoop and HDFS, I think if you're looking at that, I mean, Hadoop is majorly about to interact with HDFS, right? To actually store a lot of big data over there. Elasticsearch, the primary use case, I think we went over last session, like you can store a lot of data in it. That's evident. The primary use case is not just storage, actually. It's to search on the data. It's effectively do some analytics on top of that data. So if it is like just to primary, okay, just to store my data, no. Of course, you can do that too, but it's not just for that. I think you're talking about this, the replicas or these. There will be some zookeeper over there, and similarly we have our master node or all this cluster state that is shared among. maybe that could be something similar, but internally, or even the use case is to actually search, ability to search easily. Like simple example, right? When you're typing something, of course, Google has their own search. I'm not comparing Google, but when you're typing something else, how is the autocomplete working, right? So think about in that way. When I'm typing search, how is autocomplete working, right? Even if I misspell a word, how is it giving relevant search for me, right? If I say something called jum, Jum, right, in a kitchen related application or food related application, it actually gives me jam, right? I'm just saying in those applications, the text related search, uh, Elasticsearch is a major contender there, and also it also has other things like Elastic Stack, where it does all the fantastic things like visualizations and other major things with analytics and APM and other things. Yeah.
Cool. Anything else? Any other
Just
question?
one more
Yeah.
question. Sorry, great session, Sri. So just about the autocomplete that you just mentioned, how do you actually go about implementing an autocomplete feature? Is that something related to the setup that we do, or just one?
I'll just like I mean, yeah. So there's something called. Sorry. So this is what is. I mean, I pretty much use, for example, right? And by the way, if you're new to Elasticsearch, we would always recommend going through the Elastic documentation. So beautiful and so well acclaimed. So yeah. So with respect to your question, this is what one of the tokenizers that we would use as part of your index field. So that let's say food is your field name in a document. We actually went through mapping last time, but let's say high level, we have an object called cereal, for example, and inside that you have like food item name is a field, right? You say this field, food item field, is like type of a text, and you give this tokenizer to it. Okay, so what happens is, imagine in a scenario, this quick fox is actually jam, right? I think yeah, I think I can actually show you quickly. Okay. So I mean, this is latest version. Like for any text analysis that I want to try it out, if I'm not sure about how it looks like, I can actually use this analyze endpoint. Like if you see jam, right? So like see, it did it with 2 words. It converted it with J, it converted with JR. I mean, it's just like this is how autocomplete works. They're also like n-gram. And the reason why it does J and JA is what I want to show you next. 1 second, sorry. So to show you a difference between JAM and JAM, right? So there is like a couple of difference between edge and n-gram and h-gram. The difference is here. The first one is with edge and gram, right? If you see J and JA, it didn't bother about M, right? I think the end offset is equal to 2. That's why it didn't bother. But if you see with just n-gram, it actually is dividing, okay, J, JA, then A, AM, then M, right? The reason why I said n-gram with autocomplete is because you want, when user types J, the expectation of the application is to give all the words that contains J in the first letter, right? So that's why people use EdgeGram as one of the use case for our autocomplete feature. So you can implement that by using this tokenizer for that field called food item name that I was talking about in the serial index. Have it there, and when you're indexing the documents to that index called serial, automatically those names, those fields will go through this analyzing and analysis layer, and internally it stores as these tokens, right? JA. So even though when you type J, a call can be made to the backend to the Elasticsearch to try to find wherever this token matches. When you type JA, you can show there, okay, Jam, Jackson. I'm just breaking it up, but yeah, I think you get the idea.
Yeah. Thanks.
Yeah. Okay. Yeah.
things are so easy when you know everything behind it. So, any other question? Cool. So we'll love to see you next week. That will be another in-depth session, and see you then. Thank you. Thanks for joining today. Thanks, everyone.